You don't mind the ice cream, right?
I don't. Get the headset?
Yes.
I can talk with the ice cream. I was about to do that.
You can use this table, and there's glasses for you here that replaced it.
Oh, hi, Christian.
Okay, so welcome to the afternoon of the first day. Maciej, Antonio, and Armin will talk to us about Pypy and a life without Gil or Jill.
Hello. So if I go to my home directory and do this and press tab, I get quite a few directories of talks about Pypy at EuroPython. So you might know what Pypy is already, but in case you missed it, all those previous since 2004, Pypy is a Python interpreter written with a just-in-time compiler. It has some other features that we'll talk later, but this is the main thing. It's a fast Python interpreter. So a bit of software archeology. I'll read it aloud. I really love this sentence. Single functions doing integer arithmetic are great speedups. About anything else will be a bit slower with the JIT than without. We are working on this. You can even expect quick progress, because it is mostly a matter of adding a few careful hints in the source code of the Python interpreter of Pypy. This is as of March 2007. So more than 5 years ago, we thought that the only thing the JIT needs is, what? Few careful hints. So they were very careful, I guess. And as of now, we can say, and 3 JIT generations later, that we kind of achieved this, added a few careful hints. So Pypy is a bit old. It was started around 2003, and it was advertised at production ready in 2010. So 3 years before we advertised that we'll only need a few hints. Never tried to predict the future. And in 2010, we did the release of 1.4, which was the first one where we said, okay, this is actually something that you can use, and it should at least give you some speed ups. We also get quite a bit of funding. We got funding through the European Union Framework Program 6, which was 2003, 2007, I think. And then we got some funding through Eurostar's program. We got a lot of funding actually from donations. We're going to talk a bit about that later. But it's an old project. So what's the status now? Right now, which is 2012, we are 1.7 times faster than a year ago and quite a bit faster than 1.4. And on average, I mean, those numbers make no sense. And this is a single number representing 2 interpreters. You actually should go to the website and carefully examine all the benchmarks that got pulled into a single number. But the single number makes absolutely no sense. However, we are over 5 times faster than CPython on what we measure. So as of now, we implement Python 2.7.2. Since a year ago, we made Pypy way more friendly towards a lot more Python programs. So a year ago, it was much harder to find the sweet spot where Pypy would actually speed up your program. Now it's easier. It's still sometimes effort, and you never know. You should measure, but it's at least it's much easier. We improved since last year. Well, other people improved since last year packaging. There are packages for Debian, Ubuntu, Fedora, Homebrew, Gentoo, Arch Linux, and I'm sorry about everyone who I forgot, but their deployment situation is so much better now. It also for Windows, unfortunately the binary is only 32-bit, and for OS X. We were working about adding CPython extension support, which is only a compatibility layer. It's really hard. And it kind of works. As I can say, it moved from alpha to beta in the last year. And now it runs a large chunk of PyOpenSSL and LXML. We are about to pull the last patch that makes PyOpenSSL work. So this is the status for today, and I'm giving mic to Anto.
Oh, no, I have my phone. I have a microphone. So this was the state. Can you hear me? Yes. Okay. This was the state up to today. And in the last year, we also had some internal organization refactoring. We as a project, we entered the Software Freedom Conservancy, which is a USA-based organization which helps open source projects to continue to get money and to help with all the bureaucracy. There is Bradley, who is our reference in the SFC, who is really helping us with fighting all the bureaucracy to get, for example, tax-free donation and etc. We are very happy about this decision. Speaking on funding, we started a free campaign to get money so that we can continue working on Pypy. The free campaigns we started are one for Py3K, which means porting the Python interpreter to Python 3, one for NumPy to have a fast NumPy implementation on Pypy, and the other for the STM, software transactional memory, which Armin will talk about later. We are very happy with the status, and we would like to thank all the donors, because we collected more than $100,000 in donations, and thank you. And
who were the biggest donors?
well, the biggest donor indeed is Google, which donated $35,000 for developing Py3K. And, but also other donation came from other companies and a lot from single individuals. So thank you again to everyone. So, okay, Pypy is faster and it's production ready and etc. etc. So is it finished? No. What are two features of Python which are very helpful to developers? One is that it allows to do rapid prototyping. You can easily write a script and start it very quickly. You can run a web server in 3 seconds, where 3 is a random number. You can run your script in 0.1 second, which is another random number. And we are happy with it. Or we can use Python as a glue language. We can integrating with C libraries. We can embed a Python interpreter in a C program. And it's, quotes, easy to do it with CPython at least. So what's the status of Pypy about these things? Well, these are the two things which are a bit a problem with the current status of Pypy. Because, yes, Pypy is very fast as soon as the JIT is warmed. And the warm-up time for the JIT is significant. This is a problem we know, we are working on it, we hope to improve it. But it means that if you want to run a program which runs for half a second or 2 seconds, probably Pypy doesn't help at all. And this also means that during the development cycle, it's a bit harder because maybe if you just run your tests, it takes 4 seconds instead of 2 with Pypy than CPython. We hope to improve the situation in the next months. The second problem is that we still have no good way to call C from Pypy. Yes, there is C types, but C types is not a good way at all. And there is no API for embedding Pypy, no native API. And this is another thing we are working on, and we will talk about it later. First, let's talk about JIT warmup. So why it's a problem? As I said, the JIT code is very fast. And you can expect your Python program to go faster than CPython when it's warm. But the problem is that everything else is usually slower, in particular when the JIT is not yet working, and if the interpreter which is executing your program. So you start by interpreting, you JIT one piece at a time, and then this process takes a while. Before you ask, for technical reasons, for the way we designed it, we cannot cache JITted code between rounds. So every time you start a new program, you have to start from scratch. As I said, this is something we want to work on as a next step. If you want to know more about the internals of the JIT and why it is used warm-up time, you can come to our talk on July 4th, Pypy JIT under the hood. We will explain very technically what are the steps that the JIT does, and you will understand better what are the problems. So now let's start a bit of overview of what we did in these three funded projects. I am the main developer of the Py3K funding project. There is a branch in our Mercury repository which is called Py3K, of course. We are developing it in parallel with the other one, which means that the main one supports Python 2.7 and is not going away anytime soon. In parallel, we are developing Py3K. We are doing regular merges from default to Py3K, and this is how we are trying to develop both in parallel. So far, the focus has been on correctness and completeness. We want to have a working Py3K interpreter in Pypy and a complete one. Then, later, we will focus on optimizations, which means that at first, we will have a slightly slower interpreter than the Python 2 Pypy interpreter. But of course, this is work in progress, so you can expect progress soon. One reason why it's slower, it's because we had to drop some optimization that we wrote specifically for Python 2. For example, there are optimizations for integer versus long objects, and now on Python 3 integer objects are gone, we have only longs, and then these optimizations cannot be used directly. We have to port them, but we will do later. Other optimizations are related to string versus Unicode, and it's the same problem again. What is the status of the Py3K branch? Well, this is interesting because when I wanted to write this slide, I went to the website of python.org, I searched for the what's new in Python 3.x documents, and I started to look at the various things that there are there. And then I realized that most of them are already there. String versus Unicode, int-long unification, and all these other things you can read in the slide. I have to say that I am not the author of all of these. A lot of work on the Py3K branch comes from volunteers and external contribution. But the point is that, yes, most hard Py3K features are already implemented. So it means that you can probably take Pypy, try to execute your program, it might work. The major exception is that internally the Python interpreter still use non-Unicode identifiers, so it uses strings. And this is a problem if your program relies on Unicode identifiers with non-ASCII letters. But of course, we will solve it sooner or later. So what's left in the Py3K branch? Yes, of course, we did the first 90%, and now we just have to do the second 90%. The problem is that, yes, implementing the major features is easy, and it's also funny. But then there are tons of small issues left. So far I talked only about the core language. Of course, there are extension modules which were changed or are new in Python 3. We have to port the standard library because in the 2.7 version of Pypy we have a modified standard library, the pure Python one I mean, because the CPython standard library sometimes contains some implementation specific hacks that we have to change. So we have to port all the changes we did to the Python 3 standard library. To give a quick overview on what we did in the past months, in January there was more than 1,600 failures in Pypy own tests, and now these tests are only 83 failures. So we fixed some of those. And in January we couldn't even compile and run the CPython tests because on the Py3K branch Pypy did not compile. Now we can compile it, we can run the tests, and there are lots of failures, but most of them are easy to fix, and they should be fixed when we finish to port the changes from the standard libraries. But, okay, so this was just to give you an overview of what's happening in the Py3K branch, and we are working on it. I don't want to give any deadline to tell you when it's ready because, as I say, the small issues pop up all the time, so it's a bit hard to give an estimate. But in the next month, you should have something which you can run and try. So Maciek will talk to you about NumPy status now.
Okay, so I'm the main developer of another funded project in the Pypy 3, and this is NumPy. Progress is going, but it's going slowly, and a lot of things work, like multi-dimensional arrays, broadcasting, fancy indexing, except some corner cases. Some D-types are not implemented, but most primitive D-types work. and there's tons and tons of functions missing. So we've seen a lot of help from the volunteers, and the help typically looks like, here is a small patch that adds this function and this test for this functionality. And this patch gets pulled in quickly, and if you miss like 3 functions, you can get this going. And that way we can develop it much faster. So it's going, but it's taking time. I wouldn't even say it's 90% done, even the first one. So you can help with that. It's relatively easy if you want NumPy working on Pypy. However, it takes time. Simply, well, software takes time. So another thing, calling C. So I bet some people know this strip. If you have multiple standards, then it's better to invent a new one than use any of the old ones. So let's see on the calling C from Python landscape. We have CPython C extensions. We have sweep, seep, and another wrapper generators. We have C types. We have Cython. So what do we do? We invented a new thing, which is maybe a bit annoying, but the main goals are, so we don't want an extra language that you need to learn. For example, this is true for Cython. We don't want to, well, C-types is a mess, but other than that, C-types is working on the ABI level, which is not always what you want. C doesn't give you much security in terms of types and whatnot, but we want to use the little that it has. Like if you pass the wrong number of arguments, we would prefer a compiler error to a segfault. Well, I would anyway. So we were thinking, well, maybe we can come up with something better. So the thing is not really new. It's based on LuaJIT. And the idea is that you use the C language to declare whatever you want. And typically you can just copy-paste stuff from the header files or man pages or something, and it should work. So this is the example where you just pass a var args to a print, and it works. We also want this to work for every single library. So we want this to work for OpenSSL, which exports a lot of stuff in macros. So C-types won't work with macros unless you write some stuff in C. So we developed this thing. It's available on the read the docs where you can read documentations. And it works already pretty well for CPython, and we are developing the Pypy backend, so it will work fast on both CPython and Pypy. The goal is to make it both faster, more correct than C-types, yet dealing with most of the logic from Python and not from C or the other third language. So please go read the docs and see how it suits or does not your needs. I'll give microphone to Armin, who will talk about the third funded project in Pypy world.
Hello? Yes. Do you hear me? Okay. So the third funded project is, well, software transactional memory. Well, what is it? What do I mean by that? Remove the GIL, the interpreter lock, with quotes. I'm going to explain exactly what I mean. And the quotes. So, well, first the issue. What is the issue I'm trying to address? The problem is that, well, as you all know, with a Python program, you have one Python program, and it can run only on one core, which is of course an issue because your new laptops or servers or anything has actually now multiple cores and an increasing number of cores. So the issue is that you cannot use these cores from one Python program, even if you are using threads. So first, well, does it matter? A few quick slides. My script runs anyway in 0.1 seconds, so I don't care. Yes, but, well, the problem is that if you go with this reasoning, then the speed of your core is not going to increase anymore when the total speed in your computer is continuing to increase exponentially. So that means that, well, if I wanted to run the same script in 1982 hardware, it would take 1 hour of time. So what if the CPU speed had stopped in 1982 already? Then you would be stuck with Python, which is a language in which your scripts take actually 1 hour to run. So that's not acceptable. Okay, so the second observation or complaint about what I'm saying is that well, I don't actually have to write one program using threads. Of course, you can separate your problem in such a way that you can use a lot of processors, for example, and communicate, exchange stuff between them. Well, I would argue that there are some special cases where it is really the good answer to run several processes. Like, for example, if you have security issues or etc. However, it's not a general answer. I mean, it's not a general answer because you need to add a layer of complexity everywhere, basically, to do this cross-process communication. So, what I'm going to show here is Pypy STM, which is basically a version of Python that runs without the global interpreter lock. So, this is a special version of Pypy, and this is a benchmark. Yes, I have to give it argument. I want to run 4 benchmark steps on 4 cores. Okay, did I actually do anything? Sorry, excuse me a second. This is showing the multiple. This is showing the 4 cores on my laptops, and as you can see, it actually used all 4 cores to run this one process. And if you want a proof code that I did something, I can try to run 4 iterations of this benchmark on only 1 core. And well, that takes a bit longer. So basically, this run here is actually using multiple cores in one process. Okay, so I've shown you a version of Python without the global interpreter lock. Cool. Okay, however, it's not the first version of Python without the global interpreter lock. I should point out that there is a patch of Python 1.4 dating back to the 90s, and there is also, of course, Jython and EuroPython, which are also versions of Python that run without a global interpreter lock. So maybe a quick word about how it works internally. You have, well, it's based on transactions. I mean, software transactional memory is about using transactions in the process internally. And a transaction here means, I mean, you have to make the parallel with database. In a database, a transaction is you have your big single database and several people, several processes that all access the database. And they access it in a transaction, which means they access the database as if they were the only one currently modifying the database. The point being that if there actually is a conflict between another transaction that is also running in parallel from another actor. If there is a conflict, it will be detected. So the hope is that there is usually no conflict. And the software, or more generally transactional memory, is the same idea, but instead of a centralized database, the database is memory. The normal RAM of your computer plays the role of database, and the multiple actors are just the multiple cores. So basically, you have here, these pictures show the situation on 2 cores. If you run with a GIL, a global interpreter lock, you are running, well, 1 core after the other. And if you run with software transactional memories, they can actually run in parallel. And the point is that you may occasionally get a conflict. Here, for example, it's a situation where at this point in time, this transaction that run detects that there is actually a conflict, which means something not valid anymore occurred due to the other transaction. And then the transaction is aborted and restarted from the scratch. Okay, so, well, here I just showed Pypy STM. However, actually, it turns out that starting next year, the first Intel CPUs will come with hardware transactional memory support, which means basically with special logic actually implemented in hardware that does the same. And this has benefits on 2 levels. The first level is the speed. I mean, my Pypy STM that I showed you is actually much slower than a regular Pypy. I mean, by a constant factor, maybe 4 times slower for now. But the difference is that using hardware transactional memory, you should be able to run the same thing without much speed penalty at all, because hardware is actually doing the things like detection of detection of conflicts basically between the cores. So that means that, well, removing the global interpreter lock is actually suddenly around the corner. Next year, if you have these super modern CPUs, you will be able to run the same demo as I did, however, on CPython. However, there is one catch. The catch is that you have to use threads. I mean, threads are a mess. I will say it again. Threads are completely messy to use. You don't want to program using threads. They are messy to use at first. I mean, you need careful locks and do stuff. To ensure that basically you don't get deadlocks or something like that, or just unprotected concurrent access that end up in segfault. Okay, segfault if you were programming in C, but we are in Python, so inside you get just non-consistent and non-reproducible results, but no actual segfault, which is probably a bit better, but not much. And well, actually, parallel I like to make is the parallel with explicit memory management. If you compare programming languages that needs you to explicitly manage memory, like call malloc and free in C or C++, and if you compare this with, for example, Python or lots of other languages that come with an automatic garbage collector, I mean, it's clear that Python is better, basically. You don't have to deal with the low-level details. So the point I'm trying to make is that here, using threads is like dealing with these low-level details. So what? Well, this talk is really about there is a way to use multiple cores of your machine without using threads at all. And I will show it like this. This is an example. I mean, this is a small function somewhere in the middle of the what turns out to be the Pypy translation toolchain, which is a big program that runs for half an hour in order to compile Pypy. It's a big program that is not meant for multi-thread usage at all. I mean, it makes no sense basically to want to transform this program to suddenly become a multi-threaded program. It would be a complete mess everywhere. You would need to add lock very carefully, absolutely everywhere. So what can you do basically? This is just a loop, and this is the main loop. It calls us some function on every block of code. By block here, I mean every block in the sense of C code. So every block of every C function that is going to be generated is one of these blocks. Okay? So when you think about it, it's going to do something on each block of code, and there are tons of blocks, like 100,000 maybe in total. So it's going to do something on every block, and the point is that, well, working on these blocks is mostly independent, in the sense that if you take a random block here and a random block there, well, you can turn this block here into C code and that block there into C code. It's independent, mostly. I mean, mostly because it's not actually, because they are both. I mean, both processes, both specialized blocks, function calls are actually going to read the same parts of memory, or to update some global things or something like that. So you might get conflicts, but the point that usually you would not get conflict in this case. So how can I rewrite this function? If I just rewrite it like this is using transaction, and transaction is just a demo module that is added in Pypy. So this means just schedule all the calls and run them. And that's it, basically. What the transaction module actually does is it starts n threads, where n is depending on your processor. So it starts n threads, and it schedules the added functions to be run on these threads in any order, in random order. However, yep. So that's what you get. I mean, if we use the transaction module, and if we actually run on a Python that has a GIL like CPython, it looks like the top graphic, where f of 1 is made on one core, then f of 2 is made on one core, then f of 3 is made again on the first core. Basically, it's an example on which using threads makes no sense at all, because the total time is of course the same as running f of 1, f of 2, f of 3, just in one thread. However, if you have an STM enabled version of Pypy, it will actually be able to schedule in parallel the execution. And the point of this is that, yes, it runs in parallel, however, it does not feel to you as the writer of the code, it does not feel that they run in parallel, which means that, well, I mean, it's really just an extension of the STM ideas I explained before. It's just that they run in parallel. However, the globally observable result of this execution is the same as if they had actually run in serial order. So you can actually program in this way and pretend that the transaction module is actually running all the added blocks in serial order. That means it's a programming model that is a bit different from what we are used to, and it's a programming model that comes with the opposite catch as the one that I described earlier. The opposite catch is that, well, yes, it always gives correct results. However, you may get too many conflicts, or even systematic conflicts. By conflicts, it's really meaning it will try to run things in parallel, but they will actually conflict with each other. I mean, I can give examples, like, for example, if every transaction ends or starts by incrementing some global counter, that is one global counter, then all transactions will conflict with each other. So basically, it's not the approach I'm describing is not the perfect approach, but I still think it's a good approach because it approaches the issues from the right side. I mean, think about it. If you are using threads, it's fast. Every thread runs on its own core. However, think about it really. You have a large program using threads. If by chance you missed one point that can conflict with one other point, like you forgot one lock or something in one corner, then your program is fast, however buggy. At least sometimes it will crash and hard to debug and everything. This is the opposite. This is saying you get a programming model in which you get the programming model yes. So you get a programming model where it is correct, however it starts by being slow. It is correct in the sense it gives exactly the result you asked for. There is no possible bug in your program. Well, I mean, at least there is no bug that comes from this issue. However, it may be slow, which means that if you just apply it naively on one of your program and hope that it will work, it will probably not, because it will end in conflict. However, what I would push for at this point is that we need tools. We need better tools to help us identify when there are conflicts, which variable update we do here that conflict with which other variable updates there, etc. I mean, we need tools basically, and that's not new anyway, because you would need tools to debug your crashing multi-threaded program too. Okay. However, it's approaching the issue from the right side, which means you really have the program that works always. And by inspecting what it does with tools and putting more effort into your program, you can make it faster by actually enabling it more to use more parallelism. But yes, once again, this is the correct approach, I think, because you can start with the program that's extremely slow, and then if you do 90% of the work of removing conflicts, you get a program that is mostly fast. Now, if you do 90% of the work of removing bugs in your multi-threaded programs, you get a program that is still 10% buggy, so well. Okay, a few extra words. What is the relationship with Pypy, actually? Well, the relationship with Pypy is that Pypy is a great framework in which I can play with Pypy STM, which is the software transactional memory. It's a pure software implementation of this cross-thread detection. But if you want to do the same thing on CPython, well, if you actually have support from the hardware, then you have HTM, and using HTM, it's actually very easy to add it into CPython. So you get the CPython HTM, okay, but the catch is that the hardware transaction memory that next year is going to show up is not going to be, it's going to be enough for very short running transactions, like the transaction that occur if you just use multiple threads and keep a global interpreter lock between both. However, it's not going to work for long transactions, like, for example, the transactions that correspond to one call to my specialized block function in the example before. This is a long transaction. One call to specialized block takes maybe 1 millisecond, or maybe half a second, or this order of time. And there is absolutely no way that next year's hardware will support transactions that are so long. So that means that CPython has the problem, basically, that it's going to be stuck at this intermediate stage where internally in CPython they use HTM. However, what you are going to get is just regular threads, including all the messes that I described before, if you use threads. Yes, which is, yes. So basically, for the years to come, maybe for the next 10 or 15 years, maybe, just waving my hands here, for this time, for this amount of time, we are stuck with on CPython. You will still have to use threads. Sorry. Yes. Which really means it's annoying for Python as opposed to other languages, because other languages will get better programming models, like the one I described that does not use threads. But Python will not get the better programming model. This is all my own point of view. Or maybe everybody will actually switch to Pypy. I don't know. It's an open question.
Okay, before questions, Sooner Foldager and Martin Geisler are needed at the front desk urgently, wherever they are, if the upstairs room or here. And questions?
Two things. I see the point about long transactions, but it's kind of like the question I got this morning about big merges. Long transactions are units of work that do a lot of stuff, just like big merges are a unit of software commit that do a lot of stuff. My favorite approach, I realize that's a bit oversimplistic, is just don't do it. I mean, cut things up, fine. I do care about your explanation of why long transactions you think are the best programming model. Second point, you did mention counters, global counters, as a typical systematic conflict. I've long thought that global counters are a must and the most frequent cause of locking delays, deadlocks, and conflicts in STM, if you get that, and so on. I personally prefer to essentially dedicate thread, under the covers, to handling the global counter so that can move to message passing, essentially. You send it a message, increment, decrement, or give me the value, and it does whatever it needs internally, and it can't conflict with anybody. So I care about your opinion on these two issues.
Yes, the issue of global counters, yes, I mean, I don't know, basically. I don't have any big experience in using Pypy STM. However, well, I don't know, it's a very flexible model that I'm describing here too. So it may be that a good approach is to still use a different thread and use message passing. That's probably fine. Or I don't know. It may be that we need a few data structures that are more STM friendly, like a list on which, I mean, currently you can get a conflict if you have one list and you have two transactions that each happen one item on the same list. However, maybe with a better data structure, it could accept without conflict several additions, for example.
Like a queue.
Like
a queue.
Like a queue, yes.
Hi. Can I see the second piece of code you showed? The one with the software transaction memory again?
Sorry.
Second piece of code.
Oops.
Oops.
This was a conflict.
Yes. Sorry.
All right. So the last line, the very last line, says set update, right? Is it an
The last line, yes.
Is it an atomic operation?
This is not strictly equivalent to the. Can you move up? To this, which adds the item to the set one at a time.
Set update is now an atomic operation in Pypy.
Excuse me?
Set update, is it an atomic operation in Pypy?
So well, no, basically.
Why does this code work? The second code.
It's the second code?
Yeah.
It's in a loop.
This works because it's done after the transaction, simply.
It's not done in parallel? The whole
No, this is not done in parallel.
Okay, thank you.
I mean, this transaction.run really means on now proceeds to do the transactions. And it continues only after.
All right, so this piece is run in one thread only?
Yes, exactly.
Okay, thank you.
Any other question? There.
I'm just interested about the hardware transaction memory. Will the HTM features actually help you speed up your STM in Pypy or not really?
Yes, well, what kind of speed up are we getting from that? It is, well, I mean, as you have seen, yes, it actually speeds up. Is speed up to use STM on multiple threads, but only when you compare with Pypy that does not include a JIT. Right now, the current limitation of this Pypy STM is that it does not include a JIT. I mean, it's a matter of teaching the JIT how to generate the machine code that would actually do the conflict detection. So right now it's not usable, basically, it's just slow.
Well, to answer the actual question, how much HTM helps the STM, the answer is we don't quite know because we don't have the full specs. But it's very unlikely that the limits of transactions will actually help us right now. And there are other hardware issues, but they only released, yes, this is going to be there and these are instructions that will work. And is there software emulator yet?
No, not public.
No. So it's really hard to predict.
Mm-hmm.
When you say that CPython will be able to get rid of the GIL by using HTM, are you volunteering to do that?
Am I?
Are you volunteering to do that?
No, I know actually of at least 2 different groups that are doing it. Well, it's in some university, and then for obscure reasons they don't want me to talk about it here, so I'm not going to, but I mean, basically it's easy. I mean, if you really want, yes, I can do it. It's a matter of you see the place that does release the GIL, acquires the GIL. You replace these 2 release and acquire with generate this strange new instruction of the processor, and you are done. I really mean it. I mean, as a first approximation, and then you have to.
So I have a question. Currently in Python and standard library, there's a multiprocessor package that lets you take advantage of multi-core processors.
It's a multiprocessing package.
Yeah.
Mm-hmm.
So if you do that, you will take advantage of the multi-core processors. So
yes.
if you did that, you could still have GIL and still take advantage.
I mean, the multiprocessing package is a pile of hacks. I will say it. So the problem is that the multiprocessing, it really starts a new process, and then you need to communicate in some way or another, and then it's kind of easy for simple cases because they are nicely hiding the pickling and unpickling that you need, but that's not a general solution. I mean, if you have your two process, and then they are both accessing the same and modifying the same global dictionary, it's not going to work. They are each actually modifying the global dictionary that is in their own process, and it's your job to somehow synchronize it if you want to.
But if we could, let's take an example. Let's say we have 1,000 data blocks to process, or compilation blocks, and let's assume they're completely independent. Couldn't you just put it on a queue and then spawn the process?
Yes, maybe. But in the example I gave, it's really about Pypy translation, which really needs to read and modify global dictionaries all the time. Like
they're mostly independent.
Types or stuff.
They're not completely independent. They're mostly independent, but still the global writes, they can happen. They just can't be very often, but you still get the semantics of it working. However, if you use multiprocessing, you would start with needing 20 gigs of RAM to translate Pypy. That's the first step. Because you need to copy all the data on all the processes. Then the next problem becomes the fact that you actually do modify global data, and a problem. No, first you will hit the exception because some stuff is not pickable, like stuff with slots, and issues like this. So there are lots and lots of issues of using multiprocessing module. Yes, it works if your data is completely independent, but then you might as well do message passing by hand and multiple processing and be as good. However, if your data is mostly independent but not quite, then it's a problem. Like, I don't know, if you have web framework, you don't want to copy all the memory to access the database or something. There are different problems.
If you use multiprocessing with threads, right now I think in Python 2.7 it even deadlocks under certain circumstances, and or either crashes in segfault or deadlocks. it's really up in the air.
Not all code can be JITted, as you stated before. How does the Pypy eval loop compare with the CPython eval loop? And have you any idea about improving this eval loop?
You mean the interactive loop, the interactive prompt?
Yes, just the standard one. You fetch the bytecode and execute.
How our interpreter compares with CPython?
Well, it's mostly the same code, basically. I mean, the same structure.
Speed-wise?
Speed-wise, it's, well, I mean, our version is a bit slower than CPython. Our version is a bit slower than CPython. But that's only because it's written at a higher level of language. And then we win again because we have a JIT.
Hi there. Can you explain why you can't use software transactional memory in CPython if you've got hardware transactional memory to get rid of all the low-level stuff, like reference counting is an obvious problem?
Yes, it's the last line of this slide. It's actually a very major effort. I mean, I actually already did a few try. I mean, I wrote for fun a tiny interpreter in the same style as CPython and applied software transactional memory to it. Well, it's a complete mess, and I did not finish, etc. So what I mean is that it's not impossible. It's just tons of work, and well, if you ask me, I absolutely never see any of the Python core contributor actually going and spending the years of development on it. And yes, and then after doing it, you have all the troubles like, yes, but then all the C extension modules don't work anymore, or can only be called with the GIL, so that you need the GIL anyway, or something. It's tons of work for CPython.
I think this is it for the question time. And so unfortunately, we're run out. Thank you. So now there will be the recruiting session. Sorry for the typo on the program.